Okay, so we're going to take a look at finding the average rate of change of a function between 2 points. So what the average rate of change is, it sounds kind of scary, but it really is just finding the slope of a line between 2 points on a graph. So let's say we have a function f of x in blue, and we pick 2 points on the graph. We'll call the first point A and the second point B. And at each of those points, we have a y-coordinate where the y-coordinate A is f of A, and the y-coordinate at B is f of B. And you could think of this as like x1, y1, and x2, y2. And all average rate of change is finding the slope of the line, this slope of this red line between these 2 points. That's it. So we look at the difference in our function outputs, the change in our values of f. So this is a Greek letter delta, capital Greek letter delta, which in math typically means the change in value. So we're going to find the difference in our y-coordinates, f of b minus f of a, like y2 minus y1 over b minus a, or x2 minus x1. So this is just a variation on the slope formula that you learned way back in algebra days. All right, so example 1, we're going to find the average rate of change for each function over each specified interval. So in 1a, we have f of x equals 1 over x. So here is that graph in blue. And we're going to find the average rate of change between x equals 1 and x equals 5. So here's the point when x is 1, we get 1 over 1 is 1. And when x is 5, we get 1 over 5, which is an output of 1/5. So we're finding the slope of this line between these 2 points. So f of 5 is 1/5, f of 1 is 1. So 1/5 minus 1, the outputs, over 5 minus 1. And if we don't want to deal with this little fraction here, we can multiply every term by this denominator of 5, and that'll clear out this little tiny fraction here. And so 5 times 1/5 is 1, minus 5 times 1 is 5. 5 times 5 is 25, and 5 times 1 is 5. So subtracting them, we get negative 1/5. So the slope of this line connecting these 2 points is negative 1/5. Okay, so for example 1a, if we take a look at the graph of f of x, here we have the graph of f of x in blue, and we look at the 2 points that we're considering when x is 1, and we plug 1 in for x, we're going to get 1 in return, so we have the point 1, 1. And then when x is 5, we plug 5 into the function, and we get 1/5 in return. And so what we want to do is want to calculate the slope of the line that connects these 2 points. Now, it's actually really easy to do in Desmos because we can actually set everything up in one line. So we can either hit the / to set up a fraction, or if we're in the keypad, we can just hit division, and that'll set up a fraction as well. So if we type in f of 5, which is going to be 1/5, minus f of 1 all over 5 minus 1, we get negative 0.2, and we can change that into a fraction as negative 1/5. For part B, we have f of x equals 3x squared plus 2 times the square root of x, and then a minus 7, and we're going to find the average rate of change between 5 and 9. So if we look at f of 9 minus f of 5 over 9 minus 5, we can let the calculator do what it's good at. Because we're putting in a 5 inside of this square root, we're not going to get an approximate answer here, so we'll use that. And it's about 42.382. So sometimes you just got to round. All right, example 2, find the average rate of change between each pair of points given f of x equals x squared minus 5x plus 1. Now, we can do this in our calculators fairly easily, and I'm going to show you how to do that right now. All right, so for example 2a, we have the function f of x equals x squared minus 5x plus 1, and we're going to find the average rate of change from 3 to 3.01 on the graph. Now, if we take a look at the graph, it's a bit hard to see the red point because the red and purple points, these x-coordinates, are very close to each other. So we're going to have to zoom in a little bit so we can kind of drag this down and zoom in until we eventually can see 2 separate points. We can kind of see the 2 separate points right now. So it's very similar to finding the slope of the line connecting these 2 points, which kind of looks like finding the slope of the line of the graph itself. So if we just set up our fraction, we could do f of 3.01 minus f of 3 over 3.01 minus 3, and we find this has a slope of 1.01. So it's very, very similar, very close rather to having a slope of positive 1 as we go along this diagonal here. And if we change it from 3.01 to 3.001, change one inside here as well, notice they get closer. These are 10 times closer to each other than they were a second ago. So we're going to have to zoom in a little bit as well so we can kind of see a little bit of a difference here. But look at how small these numbers are, 3 and 3.005 over here. And if we change these ones in this fraction as well, we get 1.001. So we have 1.001 as the slope of the line connecting these two. Finally, if we zoom in even more and get the closer values of 3.0001, again, we've got to zoom in, so we'll zoom in 3 times should do it. We can kind of see those 2 points there again. Now we're really close to each other. We've got 3 and 3.002. So this space here is 0.002. So very, very close together. And if we change the values in the calculation, we get 1.0001. So notice as we zoom in, we had 1.01, 1.001, and then 1.0001. So we're going to see what happens, what our outputs, these answers here, are getting closer to. And for those of you going off to calculus in the future, this is a critical part of a majority of AB Calc or Calculus 1 is kind of what we're doing here. All right, so for part D, what value do the outputs in the previous parts A, B, and C seem to get closer to? So if we take a look at what we had for our answers, we had 1.01 for A for the average rate of change, 1.001 for B's average rate of change, and then 1.0001 for C's average rate of change. So if we look at this sequence of numbers here, they seem to be getting closer and closer to a value, and that's what we want to try to figure out is what value do these answers seem to get closer and closer to? And hopefully it's not too much for you to see that these answers, 1.01, 1.001, and 1.0001, all seem to be getting closer to 1. So for example, 2D here, those outputs seem to be getting closer and closer and closer to 1. And this is going to be something we talk a little bit about in this course, and you'll see a lot in calculus as well.